Welcome viewers to the NPTEL lecture series on the calculus of variations. This is the 7th lecture of the series. In the last lecture, we introduced fundamental concepts of the variations and related topics. We started with the concept of variation of a function f defined from the interval a to b to r, and we defined the concept of differential of this function. Here the variation delta f is actually the difference of the values of f at x plus delta x and f x. So, delta f, the variation in f is defined as f of x plus delta x minus f of x, which is actually equal to this a has to be a function of x. So, we will write the dependence of x on a like this: a of x times delta x plus beta comma delta x into delta x. So, here this beta is assumed to have this property that it tends to 0 as delta x tends to 0. So, if f is differentiable if and only if this 6.1 holds, that is the variation delta f has the property that this difference is equal to a x times delta x plus beta x comma delta x times delta x. This a will be function of x in general. So, that is what is here 6.1 holds if and only if f is differentiable, and we can see that this a actually has to be f prime x. So, this a of course is a function of x, which is the derivative of f at x, which can be seen just dividing 6.1 by delta x and letting delta x tend to 0. So, it this since beta is tending to 0 as delta x tends to 0. So, this term goes to 0, and so this tends the right hand side of this delta f by delta x tends to a of x as delta x tends to 0, and therefore, this since this delta f by delta x limit this is actually equal to by definition the derivative of f at x, and therefore, a x must be f prime x. So, we see that in the case of function we have this result that variation delta f has to be then f prime x delta x plus beta x comma delta x times delta x. This part underlying part is clearly linear in x linear in delta x, and therefore, it is called linear part in the increment of f, and this is what is called differential, and therefore, it is this differential is denoted by d f, and so therefore, d f must be f prime x delta x. And if we take f x equal to x, that the identity function, then we can see that f prime x is 1, and therefore, d x must be equal to delta x. So, for independent variable, differential is the same as the variation, and we have this d f differential of f equal to f prime x d x. This concept of differential can be extended to higher dimensions in the following manner, that f, let us say in particular we take function of two variables x y, and assuming that this f is defined from a domain in R2 into R, and assume that x y and x plus delta x and y plus delta y are points in D, then we can see that this variation d f is actually equal to f of x plus delta x comma y plus delta y minus f x y, and we say that this f is differentiable if and only if this delta f, the variation in f, that is delta f is equal to this a. So, a and b will be of course functions of x and y here, and we can see that this difference has to be then equal to a delta x plus b delta y plus beta x comma y square root of delta x square plus delta y square times delta square root of delta x square plus delta y square. So, f is differentiable if and only if 6.2 holds, and we can see that by the same process. If we take delta y 0 and then divide by delta x, we see that this a has to be actually then equal to del f by del x at x y. Similarly, b has to be, so these are functions of x y, because the derivatives are to be evaluated at x y, this at x y, similarly this at x comma y. So, these a and b are actually the partial derivatives of f with respect to x and y respectively at evaluated at x y. And so, this is the linear part in the these increments delta x and delta y. So, that is what we call linear part in the increment of the function f, and it is denoted as differential as before in the one dimensional case. And so, we denote d f, the differential of f, as f x partial derivative of f with respect to x times d x plus f y dy, since these delta x and delta y are same as d x dy. So, we get this. Now, we want to extend this concept of variation for the functionals. So, we have this functional, for example, this is our functional here. So, if we change, if we vary y, then what is the variation in I, this integral, that is what we want to define. So, here first we need to define the variation in y itself, like we had variation in x, that was delta x, and which was same thing as the differential dx. So, what is happening in this case, that is what we want to define. Here let us say y x is y x and y tilde x are two admissible functions, that means they pass through these 2 points, fixed points a and b, and then they have the property that the integral is this functional is defined. So, these y and y tilde x are admissible functions, and we want to see that what. So, the variation here in y is defined like this, delta y at x is y tilde x minus y x. So, this ordinate here, this ordinate at this upper one minus ordinate at this. So, this is the difference between those two ordinates. So, whatever is remaining inside these two is what defined as the variation delta y at x. So, if x changes over this whole interval, we have different delta y here like this, here and like this. So, it is a function of x when x varies over the interval x 1 to x 2, and then here we want to see that what is that a I y plus delta y. So, here y will be replaced by y plus delta y, and what is this y prime y plus delta y prime, that is what will also come into picture. And so, if we define delta y like this, y tilde x minus y x, clearly then delta y prime is this y tilde prime minus y prime x, and you can clearly see that this is same thing as delta y prime x. So, variation in the derivative of the variation is in this case is the variation of the derivative. So, that is how it is defined in this case, and we say that since here the concept of nearness of this y and y tilde has to be made precise, and that is what we do in the following manner. We say that this two functions, these two functions y and y tilde are epsilon close. Epsilon is a positive quantity here, epsilon close to each other in the 0 order of proximity. So, this is the order of proximity here we are defining in the following manner, that we say that y tilde x and y x are epsilon close to each other in 0 order proximity if maximum of this x 1 less than equal to x less than equal to x 2 of y tilde more absolute value of y tilde x minus y x, that is the difference between ordinates, the absolute value of that is less than epsilon for all x in the interval. So, we take maximum of this all these difference of ordinates, they should be less than epsilon. Now, we say that these y tilde and y x are epsilon close to each other in first order proximity if not only the difference between the ordinates of y, but the difference between the ordinates of y tilde are also epsilon close for all values of x. So, that is what is stated here, the maximum of x 1 less than x less than equal to x 2 of the absolute value of the difference of ordinates at x is less than epsilon. Similarly, difference between the ordinates of y prime, absolute value of that and maximum of these quantities over the interval x is less than epsilon. So, similarly, we can extend it to k order proximity in the same manner that all the derivatives y tilde j minus y j, this is the jth derivative here. So, the difference between the ordinates of jth derivative are close epsilon close to each other. So, this is I mean the difference between the ordinates of jth derivative is less than epsilon in the absolute value. So, here where j is 1 2 to n. So, for example, if we consider this y tilde x equal to epsilon sin x by epsilon and y x equal to identically 0 on x 1 less than x less than x 2, then we see that this delta y at x is nothing but epsilon sin x by epsilon. And so, absolute value of this, so absolute value of y, because y x is identically 0 here. So, this is less than equal to epsilon mod sin x by epsilon, and sin here is always bounded by 1. So, this is less than equal to epsilon. So, here we see that here we have to allow the equality also less than equal to in all these. So, we see that these two curves are close epsilon close. So, y tilde and y are epsilon close in the 0 order proximity, but this y tilde prime x is cos x by epsilon, and so and y prime x is identically 0 anyway, and so therefore, and hence this delta y prime x is cos of x by epsilon, and absolute value of this equal to absolute value of cos x by epsilon, which is only bounded by 1. And so, if we take epsilon equal to half, then we see that y tilde and y are not epsilon close to first order of proximity. They are close to they are anyway close to each other in 0 order proximity for all epsilon positive, but they are not close to each other in first order proximity if we take epsilon to be strictly less than 1. because if we take epsilon equal to half, we can see that this cannot be satisfied. This cannot be less than half in general here. So, we can see that this is an example where epsilon where y and y tilde are close to each other only in 0 order proximity. So, here we define that. So, if this I y, we say that it is I y has local maximum in local maximum at y if I y plus delta y is less than I y for delta y small. Similarly, I y has local minimum at y if I y plus delta y is greater than equal to I y for delta y small. Now, if this I y has local maximum or minimum at y for all delta y in 0 order proximity, then we say that the maximum or minimum is strong. If I y has local maximum or minimum at y for only for higher order proximity, then the minimum or maximum or a minimum maximum or minimum is called weak. Clearly, if the maximum is achieved at 0 order proximity strongly, then it is also achieved in the higher order proximity in the weak sense also. And so, but there may be cases where the closeness in the higher order proximity is required, minimum may not exist at lower order proximities, then we say that such minimum and maximums are weak. Now, here we define this variation in the same manner as we define for the function we want to extend it to the case where we have the functionals. So, first before going into that, we need to define certain concepts of linearity and so on for functionals. So, here we know that a function f from a to b to r is called linear if you have f of x plus y is f of x plus f of y for x y in a b, and f of c x is c times f x for x y for x in x y in a b, and c is in r. C is a constant in R. So, similarly, if I here a functional where it is from some admissible class defined on certain interval a to b into R. So, here A is the admissible class of functions for which this I will make sense. So, then here if you take two functions like this y 1 y 2, then it should be like this I of y 1 plus I of y 2, and this is called linear if and I of this constant c times I y. So, this is the same manner we defined where y 1 y 2 are in this A, the admissible class, and c is a number in this. So, linearity is defined in the same manner. For example, here this functional I of example here of that x 1 to x 2 here of p x y plus q x y prime dx. So, this I is linear here, I is linear. This is an example here of this. Next, we define the continuity. So, recall the continuity. So, f from a to b into r is called continuous if continuous at x belonging to a b if for every epsilon greater than 0 there exists delta which is a function of epsilon as well as x, and this is also positive, such that for y minus x less than this delta implies f of y minus f of x is less than epsilon. So, here it is like this a and b and function here, let us say at this point what should happen at this point x. If we take a neighborhood around this, all y's in this, so the delta neighborhood delta, this is x minus delta to x plus delta. In this interval wherever that y is there, this f x is here, this is f x. So, and this is epsilon strip, this is f x plus epsilon, this is f x minus epsilon. So, here these values f y must lie within this strip. So, and this is what is like this, sorry. This x minus delta to x plus delta strip. So, this point x f x or y f y must lie, this is x f x, and here. So, within this rectangle these values must lie, y f y must lie here, y comma f y, this point must lie within this rectangle. So, that is what it means. If we have these values sufficiently, these values y sufficiently close to x, then the values f y will also be lying sufficiently close here in this y strip. So, that is what is the continuity of a function. So, here the continuity of a functional we will be defining in this following sense. So, here if we consider this I y, so I y will be continuous at y if we consider this neighboring variations. So, this is delta I, so if we take this delta y sufficiently close to, so this, so I is called continuous at y if for every epsilon greater than 0 there exists delta which will be function of this and y here, such that this absolute value of I y plus delta y minus I y will be less than epsilon. So, it is extended in the same manner as the function case. So, the continuity of this functional is defined in the same manner. Now, we want to define the variation of a functional So, we have already considered this I y and I y plus delta y, the difference between them. We say that as we define variation of a function, we say that the variation delta I of a functional I exists if the following holds: if this delta I has the form which is nothing but delta at delta, it will be a function of y, this I y plus delta y minus I y, this has the form that there is a linear part here, it is function of y as well as delta y and plus beta y delta y, and then the absolute value of the maximum times maximum of delta y. This maximum is taken over the interval maximum over a b, where I is defined, such that this beta y comma delta y tends to and tends to 0 as delta y tends to 0, and this L is linear in delta y. So, we say that this is 7.1 we will call. We say that the variation of functional I exists if and only if 7 point holds, that is the delta I, that the difference I y plus delta y minus I y has the form that there is a linear part in the increment, that is L y delta y. This is linear in delta y, plus here the term beta y comma delta y times maximum of absolute value of delta y. This maximum is taken over the interval where this I functional I is defined. So, we say that this variation exists if and only if 7.1 holds. Now, here there is another way of defining, equivalent way of defining the functional variation of a functional, another equivalent definition of the variation. For example, in the case of a function, we know that this d f we had defined d f equal to f prime x delta x or the same thing as f prime x dx. Here we can see that this is also equal to, if we consider f of x plus alpha delta x and differentiate it partially with respect to this and evaluate it at alpha equal to 0. This is the same thing as f prime at x plus alpha delta x, and then this argument differentiated with respect to alpha gives you delta x. This thing evaluated at alpha equal to 0. So, this gives you f prime x delta x, which is same thing as f prime x dx from here. So, this is a convenient way of defining equivalent way of defining the differential of f. Same way, if we imitate this definition for the functional, we can consider in the following manner that we consider here delta I y as I y plus alpha delta y minus I y. So, this will be then equal to, if variation exists, then from 7.1 this should be equal to L y alpha delta y plus beta y alpha delta y, and mod alpha maximum of delta y, and here if we divide by this. So, if we divide by this here, delta alpha, and then take limit delta alpha tending to 0, is same thing as limit delta alpha tending to 0. This is delta alpha of delta I y upon alpha, because delta alpha is alpha minus 0, which is same thing as alpha. And so, you since this L is linear, we see that this will give you y delta y plus, here you will have beta y alpha delta y, and here you will have alpha over this maximum mod delta y. And since this quantity is bounded, this quantity is bounded, and this quantity goes to 0 as delta y, as since alpha tends to 0, therefore, alpha delta y will tend to 0 as alpha delta y tends to 0. And so, this will be equal to this, the whole thing, limit of this delta alpha tending to 0 of the whole thing. And so, this will be equal to L y delta y, which is the linear part in the variation. This is the linear part in the variation, of the functional. And so, this is what will be actually defined as so, this hence we define as we defined the differential. As we define the differential, we define variation delta I as L y delta y. Here this is, we should change this notation here, this is delta I at y. This also will change to delta, so that we use different notation for the variation and the difference. Similarly, here let me correct that. Okay. So, here also we change this to delta. So, this is the difference, this capital delta will be used to define the difference between the values at y of the functional I at y plus delta y. This delta is used for variation. So, this is a variation of the function y itself, and this is the difference in the values of the functional. And we say that if variation exists, this variation we will be defining as delta I. So, here we say that the variation of the functional exists if and only if the 7.1, which means that the difference is equal to this linear part in the increment, that is L y comma delta y plus beta y comma delta y times maximum of absolute value of delta y. and we see that provided this beta goes to 0 as delta y tends to 0, we say that the variation of I exists, and we as we define the differential of a function, we define here the variation of this functional, the linear part in the increment. So, that is what we have in the case of the functional. Now, here we will consider in the same manner as we consider in the function case, we can have equivalent definition like this, that equivalently we define this I y plus alpha delta y and then partial derivative with respect to alpha and evaluated at alpha equal to 0. This is what we have seen in this case as the variation, and so this is what will be called the delta I at y. So, this is what equivalent definition is very convenient to use. This is what we will be using subsequently in our lectures. Now, let us consider here the case of the simple first, which we considered this I of y, which is actually equal to x 1 to x 2 f x y x y prime x dx. So, we would apply this equivalent definition here of the functional, the variation of the functional, and we will see that we will consider here I of y plus alpha delta y, and then we will differentiate it with respect to alpha, and then we will equate that to 0 and see that the condition which is to be satisfied by the function y is what we will be getting as an the necessary condition for this y to optimize this functional, and that is what will be giving us the Euler equation, which is to be satisfied by the function y in order this functional to be optimized. So, that is what will be considered in the next lecture. Thank you very much for viewing this.